Welcome to Understand the Math. Before you begin, be sure to check out the video description below for a link to free guided notes that you can download and fill in as you watch this video. This is the fifth part of a 7-part series on topics that commonly appear on an introductory linear algebra midterm or final exam. This video goes over 6 topics related to vector spaces. I'll begin by talking about linear independence and working through an example problem. A set of vectors is linearly independent if neither of these vectors can be expressed as a linear combination of the others. Let's try to first understand this from a graphical perspective. Our first picture shows 2 vectors that are linearly independent. Let's label these vectors v1 and v2. And we'll mark down that they are linearly independent. Note that these 2 vectors do not point in the same direction or in opposite directions. Our second picture shows 2 vectors that are linearly dependent. We'll label the first one v1 Note that these 2 vectors point in the same direction. To understand linear independence from an algebraic perspective, we say that a set of vectors is linearly independent if the equation k1v1 plus k2v2 all the way up through krvr is equal to 0 has only the trivial solution. I'm going to highlight this equation in green. And I would suggest that you memorize this equation because this is the equation that you need to start with when you're trying to test whether or not vectors are linearly independent or linearly dependent. Let's now connect the geometric definition with the algebraic definition. In our first picture, v1 and v2 are linearly independent. That means that k1v1 plus k2v2 is equal to 0 will only have the trivial solution. Let's see what that looks like. We're going to plug in v1 and v2. So v1 is 1, 1. And then v2 is minus 1, 2. And let's set that equal to 0, 0. To solve for k1 and k2, because that's the solution we're looking for, this is a scenario where we're supposed to only get the trivial solution, so k1 and k2 should equal 0. Let's see if that works out. We'll form our augmented matrix. And we'll put our matrix in echelon form. Our second row is 0, 3, 0. We have a pivot in every column, so that means that k1 and k2 are going to equal 0, and we only have the trivial solution. Let's summarize this here. Each column has a pivot. So that tells us that we have only the trivial solution. Which tells us that k1 is equal to 0 and k2 is equal to 0. So that is algebraically how you can determine if 2 vectors are linearly independent. So v1 and v2 because we got the trivial solution as our only solution, v1 and v2 are linearly independent. In our second picture, v1 and v2 are linearly dependent. This means that this equation, k1v1 plus k2v2 is equal to 0, should have solutions in addition to the trivial solution. Let's see what that looks like. We're going to plug in v1 and v2 from our second picture. v1 is 1, 1, and v2 is 2, 2. And we set that equal to our 0 vector. We'll form our augmented matrix. And we'll put it in echelon form. We see that our matrix has only one column with a pivot, and we have one column that's missing a pivot. This gives us K2 is our free variable, and K2 can take on any value from minus infinity to infinity, so that gives us infinitely many solutions. So we have the trivial solution and also infinitely many more solutions. So we do not have just the trivial solution. So that tells us that our two vectors, v1 and v2, are linearly dependent. Let's now look at an example where we're given a set of vectors and asked to determine if they are linearly dependent or linearly independent. The procedure is going to be that we're going to put our vectors in an augmented matrix like this, and we're going to reduce it to echelon form. And then we're going to check to see if every column has a pivot. Our matrix looks like this. And I'm going to skip the reduction steps. And this is what we end up with. Notice that we have a pivot in every column. That tells us that our vectors are linearly independent because we only have the trivial solution. If A is a square matrix, we can also check the determinant. If the determinant of A is not equal to 0, that tells us that we have a unique solution, and that solution is x is equal to 0 because our right-hand side is 0, which means that our vectors are linearly independent. If you're finding this video helpful, please give it a thumbs up and drop a comment below. I'll now explain what a basis is and go over an example problem. We'll begin with a vector space that's shown in blue, and we'll label this as vector space V. Within our vector space, we have a subset S that's denoted in purple. Our subset S contains the vectors v1 all the way up through vr. Our subset is a basis for a vector space if two things happen. The first thing is that S is linearly independent. In other words, our set of vectors are linearly independent. Our second requirement for a subset to be a basis for a vector space is that the subset spans V. Let's look into both of these requirements a little bit further. We can say that S is linearly independent if K1 V1 all the way up through KR VR is equal to 0 has only the trivial solution. This means that the vectors in a basis do not depend on each other. For the second requirement, S spans V if every vector in V can be written as a linear combination of the other vectors. This means that K1 V1 plus K2 V2 all the way up through KR VR is equal to B has a solution for every B. To see if both of these requirements are satisfied, we have to form a matrix A made up of our vectors V1, V2, all the way up through VR, and we have to take that matrix and put it in echelon form, and then see if every column has a pivot. Let's now do an example where we have to determine if the vectors form a basis for R3. We already know that E1, E2, and E3 form the standard basis for R3. Now we're going to figure out if these vectors can also form a basis for R3. Our matrix A is going to look like this. We put V1 in the first column, we'll put V2 in the second column, and then we'll put V3 in the third column. We'll then reduce this to echelon form, and I'm skipping steps here, and we end up with this matrix. Let's now highlight our pivots, and we see that we only have two pivots. Our third column is missing a pivot. That tells us that one vector in this set of vectors can be written in terms of the other vectors. So our vectors are not linearly independent, which means these three vectors do not form a basis for R3. So we'll write down a no. Let's now talk about coordinate vectors and do an example problem. We're going to let S be equal to the set of vectors E1, E2, and E3, and this forms our standard basis for R3. This means that any vector in R3, given by our vector v, can be written as a linear combination of these vectors. Our coordinate vector of v relative to s can be written in two ways. The first way is in column vector form and looks like this. It's going to be k1, k2, k3. From that linear combination right there. Or we can write it in comma delimited form like this. Let's now let S be a set of vectors v1 through vr, and this is a basis for RR. This means that v, any vector in RR, can be written as a linear combination of these vectors. The way we would write the coordinate vector for v looks like this. We would write it k1, k2, all the way up through kr if we're writing it in column vector form, or we could write it in comma delimited form like this. k1, k2, all the way up through kr. Let's now put this theory into practice and do an example problem. In this example, we're asked to find the coordinate vector of v relative to our basis vectors v1, v2, v3. We'll begin by writing down the equation for v. So v is k1, v1 plus k2, v2 plus k3, v3. What we're doing is we're expressing v in terms of our new basis vectors. To find v sub s, which is given by our k's, we have to find our k's. In order to find the k's, we're going to write this equation in matrix form. So we're solving for the k's, so we write down our v's. So v1 goes in the first column, v2 goes in the second column, and v3 goes in the third column. We then augment that with v, 5 minus 1, 9. We have to put this in reduced echelon form. So when we do that, I'm skipping the steps. It looks like this. On our left, we're always going to get the identity matrix, and on our right, we end up with this. This tells us that our coordinate vector is equal to 1, minus 1, 2. This means that we would write 5 minus 1, 9 if we're in the E1, E2, E3 coordinate system. And we would write 1, minus 1, 2 if we are in the V1, V2, V3 coordinate system. Our next topic is the row space, column space, and null space of a matrix. I'll explain what these three subspaces are, then do an example where we have to find these three subspaces. And lastly, I'll explain how to find a basis for these subspaces, and we'll do another example. We'll start with a rectangular matrix whose dimensions are m by n. That means it has m rows and n columns. Let's first look at the row space of A. A has m rows, and most importantly, n entries in each row. The row space of A is written as row of A, and it's equal to all linear combinations of the rows of A. We say that the row space is a subspace of Rn spanned by the row vectors of A. Notice that these two match up. We have n entries and it's a subspace of Rn. Let's now look at the column space of A. A has n columns and m entries. We abbreviate the column space as COL of A. And the column space is equal to all linear combinations of the columns of A. Our column space is a subspace of Rm, and it's spanned by the column vectors of A. Notice that these two are connected. We have m entries in each column, so our column space is a subspace of Rm. The last subspace that we'll go over is the null space. To understand the null space of A, we need to look at the equation AX is equal to 0. When we solve this, our X is an element of Rn. Our null space is abbreviated by null A. The null space is the solution X to AX is equal to 0. I'll put a star right there because I know that students will often have a difficult time remembering what the null space is. It's the solution X to AX is equal to 0. Because X is an element of Rn, the null space is a subspace of Rn that is the solution space of AX is equal to 0. Notice the connection that these are the same. We'll now do an example. We're going to find the row space, column space, and null space of matrix A. We'll begin with the row space. The row space of A is going to be all linear combinations of the rows of A. So we can write this as K1 times our first row plus K2 times our second row plus K3 times our third row. Our column space of A is all linear combinations of the columns of A. That looks like this. The column space of A is going to be K1 times the first column of A plus K2 times the second column of A plus K3 times our third column of A. Notice that both the row space and the column space contain an infinite number of vectors. The null space of A is all solutions X to AX is equal to 0. So the null space is going to take more time to compute than the row space and the column space. So what we're going to have to do is we're going to take our matrix A, we're going to augment it with 0, and we're going to take this matrix and place it in reduced echelon form. And find X. Our matrix looks like this. We'll augment it with 0. And then I'm going to skip all the steps, and we're going to put it in reduced echelon form. And that looks like this. This means x1 minus x3 is equal to 0, which gives us x1 is equal to x3. The second row tells us that x2 plus 2x3 is equal to 0. And this gives us x2 is equal to minus 2x3. Putting this all together, we get x is x1, x2, x3. And then we'll plug in what these are equal to. So we have an x3, a minus 2x3, and then an x3. And we'll pull out the x3, and we have the vector 1, minus 2, 1. This vector is our null space. Notice that our null space also contains an infinite number of vectors because our free variable x3 can take on any values between minus infinity and infinity. Now that we know how to find the row space, column space, and null space of a matrix, we need to learn how to find the basis for these subspaces. The basis for a subspace is a smaller finite set of vectors that is easier to work with than the full subspace. I'm going to demonstrate how to find a basis through this example problem. In this example, we're asked to find a basis for the row space and column space of A. Notice that this is the same matrix that we were working with on the previous page. To find the basis for the row space or column space of a matrix, we're going to begin by taking our matrix A and putting it in echelon form. That form looks like this. Our second step is that we're going to locate the pivot columns of A and our non-zero rows of A. We'll highlight in yellow our pivot columns of A, and in green, we'll highlight the non-zero rows of A. The basis for our row space is the original rows of A that correspond to our green highlighted rows. So our basis looks like this: 1, 2, 3, 4, 5, and 6. The basis for our column space is made up of the original columns of A that correspond to our yellow highlighted columns. Those are our columns that contain a pivot. So we have 1, 4, 6, and then 2, 5, 7. In our last example, we're going to find a basis for the null space of A. Again, we have the same matrix that we had on the previous page. Our first step is that we're going to take AX is equal to 0, and we're going to put this in reduced echelon form. The second step is that we're going to find x. We actually did all this in the previous page when we found the null space. So I'm going to write down our solution that we had obtained. We found that x is equal to x3 times 1 minus 2, 1. So our basis for our null space contains this vector x, but not the free variable. So our basis looks like this. 1 minus 2, 1. I want to make a note that the number of vectors in the basis for the null space is equal to the number of free variables. That's going to be important when we talk about dimension, which is our next topic. I'll now define what dimension is and go over 2 example problems. The dimension of a finite vector space V is the number of vectors in a basis for V, and we denote this by dim of V. It's really important to note that it's not the number of vectors in the vector space. It's the number of vectors in the basis for the vector space. In this first example, we're going to find the dimension of the row space, column space, and null space of our matrix A. I wrote down in green what we had gotten from the previous page. We had the basis for the row space, the column space, and the null space. Now what we have to do is find the dimension. So the dimension for our row space of A is going to equal 2 because it's the number of vectors in our basis. Same thing for the column space and null space. We'll say the dimension of the column space of A is equal to 2 because we have 2 vectors in that basis, and then the dimension of the null space of A is equal to 1 because we have 1 vector in that basis. Let's make a note that the dimension of the column space of A is the number of pivots, or more precisely, the number of pivot columns in A. The dimension of the null space is the number of free variables in our matrix A. In our next example, we're going to determine the dimension of the subspace H of R3 spanned by the vectors v1, v2, v3. To find the dimension of our subspace H, we have to place our vectors v1, v2, v3 into a matrix A. We then have to reduce that matrix to echelon form. And we're going to count the number of pivots. When I give linear algebra exams, this is probably one of the most missed problems. And I think it's because it's difficult to remember how to actually set this problem up. So our matrix A looks like this. It's 2 minus 8, 6, 3 minus 7 minus 1. We're placing V1 and V2 and V3 into A. And then I'm going to skip steps. And if we put it in echelon form, it looks like this. Let's now highlight our pivots. And we see that we have 2 pivot columns, which means that we have 2 linearly independent vectors, which gives us that the dimension of H is equal to 2. The last topic that we'll go over in this review is on the rank of a matrix and the rank theorem. The rank of a matrix is really important because it measures the redundancy in a matrix. The rank of a matrix is equal to the number of pivot columns of A. That number is always less than or equal to the minimum of the number of rows or the number of columns. In this example, we're going to determine the rank of A. Let's notice that our matrix A has 2 rows and 3 columns. So that means that our rank has to be less than or equal to 2. I'll write that down. What we're going to do to determine the rank is we're going to take our matrix A and we're going to put it in echelon form, and we're going to count the pivots. Our matrix A, if we put it in echelon form, looks like this. Let's highlight our pivots, and we see that we have 2 pivot columns. So that means that our rank is equal to 2. So we'll write that the rank of A is equal to 2. Let's now go over the rank theorem. Our rank theorem relates the number of pivot columns to the number of free variables to the number of columns in a matrix. Let's remind ourselves that the number of pivot columns is the dimension of the column space of A, or it's the rank of A. The number of free variables in our matrix A is the dimension of the null space of A, or sometimes it's called the nullity of A. And then the number of columns of our matrix, and we're going to assume that our matrix A is m by n, so the number of columns is equal to n. Our rank theorem then looks like this. The number of pivot columns of A plus the number of free variables in A has to equal the number of columns in the matrix. We write this as rank A plus nullity A is equal to n. I'm going to use this first example to show you how the rank theorem works. This is the matrix we've been working with. Let's write down what it looks like in echelon form. I'm going to highlight our pivots in yellow, and I'm going to highlight the column that we get our free variable from in green. So our number of pivots is equal to 2. Our number of free variables is equal to 1, and our number of columns is equal to 3. So our pivots plus our free variables equals our number of columns. In this last example, we're asked if a 4x3 matrix has a rank of 2, what is the nullity of the matrix? Let's begin by writing down our rank theorem. We have the rank of A plus the nullity of A is equal to n. Our rank of A is equal to 2. The nullity is what we don't know. And then n is our number of columns It's a 4 by 3 matrix, so that means we have 3 columns. So that tells us that the nullity is equal to 1. You may want to check out the next video in this series. It's on eigenvalues and eigenvectors.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.